Hello, my name is Joseph Dolan and this is my paper presentation on a framework for automated reverse engineering of industrial control system binaries. I want to acknowledge the original authors of this paper and the work behind it, Anastasios Kalaris and Michal Maniatakos from the New York University. This work was presented at the NDSS Symposium in 2019 in San Diego, California. Below are the links to the original paper and the GitHub repo of the framework. The goal of the research is to create a framework to reverse engineer industrial control system programmable logic controller binaries compiled in the Codesys IDE to enable digital forensics and incident response teams to review and analyze PLC malware without needing expertise in the manufacture of specific products and software suites of the PLCs. The Codesys IDE was developed based on the IEC 61131 standard for PLC programming languages, as this is the best commonality across manufacturers, and its goal is to provide a hardware-independent development environment for PLCs. It also provides users the option to port code from one PLC brand to another. The I/O mapping addresses would need to be updated in that scenario. This will enable response teams to deploy countermeasures in a timelier fashion. This framework could also be used by bad actors to create dynamic malicious payloads, which could be deployed more easily without C2C infrastructure, as demonstrated in the case study in the results section. The differences between conventional binaries and PLC binaries. The execution model. Conventional binaries follow sequential execution, whereas PLCs infinitely execute their three comprising steps dictated by the scan cycle, shown in Figure 1. This can hinder dynamic analysis. I/O operations are significantly higher in PLCs, occupying 2/3 of the scan cycle. The binary file formats are not well documented for PLCs. PLC compilers make very conservative optimizations. These differences are due to the mission-specific tasks related to PLCs. There are many PLC and control system manufacturers on the market, most of which utilize dedicated software and graphics packages to engineer and use their products. To investigate any attacks on an ICS, the investigator needs to be a subject matter expert on the specific manufacturer's systems and software tools. Even with this knowledge, the process is a manual and time-consuming one. The IEC 61131 standard was published in 1993 with the goal of standardizing PLC programming languages for ICSs. The Codesys IDE version 1 was released in 1994 with the goal of giving ICS programmers one software tool to use across multiple hardwares. Figure 2 on the right shows some of the PLC brands on the market, but this isn't a complete list, and even with this list, under some of the brand names like Honeywell, there are multiple offerings. The solution was split into two phases, the platform-specific phase shown in Figure 3 and the automated binary phase shown in Figure 4. The platform-specific phase had two steps. Step 1, learning to understand the proprietary undocumented binary formats of these manufacturers, and Step 2, create two knowledge DBs, one for the I/O mapping information and one for the known functions information. The automated binary phase had three core steps: dissection of the binary into its comprising components, control flow graph reconstruction, and I/O and operations functions identification. There were three supplemental steps: the automated extraction of the functional arguments, the binary modification, and the control flow graph visualization for verification. These will be looked at in detail in the following slides. The platform-specific phase, Step 1, learning the binary formats. These binaries include headers, code and data sections, symbol tables for dynamically linked code, etc. The team used reverse engineering techniques from embedded systems and file format analysis to assist the process. A key feature of PLCs is they are real-time systems, and therefore the compiler optimizations are conservative, which aids the reverse engineering process. The team used the WAGO 750-881 PLC, which uses an ARM microprocessor. They developed some programs that perform simple tasks to establish a baseline for the binaries. The investigations indicate the findings are representative for all hardware programmed with the codices with minor I/O mapping modifications required. Figure 5 on the right shows a list of all the PLC manufacturers and the development platforms used. The platform-specific phase, Step 1 findings. As can be seen in Figure 6, the first 80 bytes make up the header. The entry point for the program was identified. Only part of the header needs to be reverse engineered to enable automated analysis. The subroutine delimiters were identified. The entry and exit instruction sequences were identified as shown in Figure 7. Initialization of global variables in generic subroutines. The first subroutine, global init, is located at offset 0x50 after the header. This subroutine sets constants, variables, and initializes functions defined in the var global section of the IEC 61131-3 program. After that, there are 3 short subroutines followed by the debugger. Continuing on, the statically linked libraries and user-defined function blocks. The debugger is followed by subroutines for imported library function blocks. The statically linked function blocks consists of 2 subroutines, one to perform the main functionality and one that initializes the local memory. Custom function blocks that correspond to code directly developed by a PLC programmer are placed after the library function blocks. First, the subroutine that performs their main functionality, followed by its initialization subroutine. The team also identified the penultimate subroutine to be the main function, a user-defined function block named PLC_pro PRG in codices. This subroutine is mandatory and serves as the starting point of the scan cycle. Finally, the symbol table. The symbol table contains information about standard functions such as math operations, which are dynamically linked in codices. The table contains string IDs followed by 2 bytes of data, which are used to calculate the jump offset required for calling the corresponding function, as shown in Figure 9. The platform-specific phase, Step 2, creating the I/O database. The inputs and outputs of the PLCs are mapped to addresses, which the PLC calls when it wants to read a sensor and writes to when it wants to move or change an actuator. The Wago 750-881 PLC has an input and output address range as shown. These addresses are different for each PLC, however that information is contained within a trigger file in the IDE installation directory. The team was able to parse the trigger files and use the information to populate the I/O database in an automated manner. Moving on to creating the known functions database. This database contains signatures of known library functions and code snippets. This known functions database contains information pertaining to standard functions and libraries that can be statically linked in the binary. IEC 61131 programmers can import and utilize library functions and function blocks in conjunction with custom functions and function blocks. Typical examples include functions that handle network communications, such as the Modbus SMTP stacks, common control algorithms like PID loops, and timing functions. Similar to typical programming paradigms, identifying and fingerprinting these functions can speed up the analysis of a given binary, as the reverse engineer will not have to spend time understanding already known functions. The team created fingerprints of the statically linked library functions using the binary layout knowledge gained in the platform-specific phase. They created 1,704 binaries, one for every function block included in the 212 libraries that are available in codices. The team selected opcodes and discarded instruction arguments and verified in their experiments the sequence of opcodes defined the functionality of the subroutine. The automated binary analysis phase. This process is split in two, with the core steps executed first, followed by the supplemental steps as shown in Figure 4 on Slide 7. The first core step includes breaking the binary into its components using the information gathered in Step 1 of Phase 1. The subroutines are delimited and disassembled, the code data sections and symbol tables describing dynamically linked functions are identified. The second core step reconstructs the control flow graph with the information available. The final core step utilizes the DBs created in Phase 1 Step 2 to identify the I/O operations and the known functions. Moving on to the supplemental steps, the first supplemental step augments the resulting analysis and allowed further automation. This automated extraction of arguments passed to function calls was done using dynamic binary analysis techniques and symbolic execution. This step was leveraged to extract semantic information regarding the process that the PLC binary is controlling. It can also assist in recovering lost source code. The second supplemental step considers the modification of binaries. This enables overriding the contents of any location in the PLC binary, which can be used for dynamic payload generation or injection of host-based defenses. The final supplemental step provides an intuitive representation of the results, including the control flow graph visualization created in .graph description language, where each subroutine and dynamically linked function is a node and calls between them are edges as shown in Figure 11. As can be seen, Figure 11 shows the visualization of the call graph of a PLC binary that controls part of a chemical process using two PI loop controllers. The blue edges are calls to statically linked functions, the red edges are calls to dynamically linked functions. The edge weights represents the number of calls, so it can be seen from the diagram that the PLC program calls the PID fixed cycle routine twice. The results were easily verified as the team essentially had a golden copy of the PLC binaries used for the analysis. A line-by-line comparison of the results against the program's source code was carried out, verifying the match for all the binaries tested. The 1704 binaries created earlier for the known functions database were excellent samples to verify the preliminary tests for the framework. In all cases, the results matched the control flow graph 100%, validating the correctness of the reverse engineering. Subsequently, in-house developed binaries were produced to evaluate the framework. A program was written to control a section of a chemical process. The program had two PID loops that executed in a fixed time interval and a digital input that triggered on rising edge that activated the PLC execution using an external signal. The resulting reverse engineering visualization is shown in Figure 11 on the previous slide. A further 471 CodeAssist project files were downloaded from 127 repositories on GitHub. The target PLC models were identified by examining the strings contained in the project files. The quantities obtained are shown in Table 2. 235 of the 471 were from a single source that provides control solutions in the energy sector. The other programs covered a wide range of industries, including building automation, automotive industry, robotics, etc., as well as covering all the 61131 programming languages. This diversity strengthens the framework database's ability. Of the 471 programs, 266 were analysed and verified after discarding the non-useful ones, i.e. ones with corrupted, too simplistic or non-functioning. The framework performance was evaluated from a time standpoint. It's important the reverse engineering process can handle PLC binaries of various sizes and complexities. This was assessed using the time taken at the required steps for the 266 PLC binaries obtained from GitHub. This was done by measuring the time spent in disassembling the subroutines with Radar 2, constructing the call table with Anger, and the total time required to analyze a binary. Figure 12 shows the times ranging from 20 plus seconds for small files to 80 plus seconds for files upwards of 550 kilobytes. The results demonstrate the scalability of the framework, which will easily complete a 2 megabit file in under 5 minutes given the linear nature of the relationship between the file size and the time required. The team carried out a case study to demonstrate how the framework can be used to create and deploy dynamic payloads. The case study consists of two actors, an attack designer and an attack deployer. It assumes the attack designer has technical capabilities and the attack deployer has access to the target environment but lacks the technical skills to develop the attack. The scenario demonstrates how the attack can be bundled into a smartphone and deployed. The case study used a modified version of the Tennessee Eastman chemical process simulation model connected to a Waco PLC as shown in figure 13. Also shown in this is the smartphone used to deploy the payload. The TE simulator is a realistic simulation of a chemical process released to the academic community as a benchmark. An LG Google Nexus 5 running the Ubuntu Touch operating system was used to deploy the payload. The attack is designed in such a way that the deployer only needs to establish a connection to the network, either wired or wireless, and deploy the attack using a simple push-the-button application. Powered by the automated reverse engineering capabilities of ICSREF, the smartphone can understand the structure of the PLC binaries, make inferences regarding the physical characteristics of the controlled process, and generate modified binaries that deploy meaningful and impactful attacks in an unsupervised and autonomous way. The phone was programmed to carry out a sequence of steps to identify PID loops and modify them as shown in figure 14. In summary, the phone scans the network of PLCs, fingerprints them and downloads any binaries they contain within approximately 90 seconds. Subsequently, the binaries are automatically analyzed with ICSREF. During this step, ICSREF identifies whether the binaries contain any PID loops, extracts their arguments, and modifies them accordingly, generating modified binaries. Finally, the modified binaries are uploaded back to the PLC, and a soft reset command forces the PLC to execute the malicious code. The attack altered the proportional gain of the loop, increasing it by a small constant relative to its previously programmed value. The change caused the reactor pressure to stabilize at a lower pressure set point at around 2350 kPa instead of the optimal value of 2800 kPa. The impact on the reactor pressure is shown in figure 15. Since this change does not cause any of the measured variables to go out of range, it will not trigger any alarms. This proof of concept demonstrates how ICSREF can be used by bad actors. That concludes my presentation. Thank you for watching.